conductor. Then we join those two pieces together to form a PN junction that we call diode. How we bias that diode, what are the other kinds of diodes, only in brief. And then we went on to discussing transistors. In transistor, we just discussed the NPN bipolar junction transistor. Then we use that transistor in a circuit, we call it amplifier. How we chose the components to design a distortion-less amplifier. I'm hoping that this will cover all this morning, and then we will go have 1 hour and then come back and just spend the rest of afternoon on op amps only. So does that sound good?
Mm-hmm.
Very good, very good. So before we start, is there any question, any concern, anything that you'd like to discuss?
I got one. It's a really basic question, just going back to like our conductors themselves. Like when we overdope, why again does it ruin the material when we put too much dopant?
Very, very good question. Very good question. So if I may just answer this before we go into that, although I would somehow arrive at that, I hope. You see, when we have a piece of semiconductor, this piece of semiconductor, we can call it silicon for now. I mean, there are other forms of semiconductors, but silicon is the simplest. And there are 10 to power 22 atoms per cubic centimeter in that piece of silicon. So if I have a piece of silicon, now I want to dope this with, say, N-type. I want to make it N-type. Now, when I want to dope it, I have to put this inside what's known as a furnace, which is very, very hot atmosphere. So I bring this to an elevated temperature. And because it's hot, obviously the atoms are very loose and they vibrate easily. And then I also prepare some gas of the dopant, for example, phosphorus or antimony, or what was the next one? The N-type, antimony, phosphorus, and what was the other one? Oh God, phosphorus, antimony. Oh, I forgot. Anyway, those, yeah, those.
I was gonna say it wasn't like arsenic or
arsenic.
uranium,
Thank
right?
you. Arsenic. Thank you very much. Arsenic is the other N-type. So bringing the gas in the form of arsine or phosphine or these kind of things into that chamber, into that closed furnace, tube of absolute vacuum, and we bring this gas in. So now the arsenic will diffuse inside silicon and get the home atom, the host atom. They get the host atom out of their place and they sit in their place. When we will only call it doped, the dopant takes place once this process is done. So if arsenic enters the structure of silicon but does not sit in the place of somebody's, who is it? Okay. If arsenic enters the structure of silicon but does not replace a silicon atom, we don't call that dopant. That's not dopant. So dopant is only when the arsenic atom goes and replaces the silicon atom. Okay, and by doing this, there will be an electron free electron. So the number of arsenic atoms which enter the silicon and free one electron each, that is the number of dopants. So we can say 10 to power 18 or 10 to power 19 arsenic atoms have arrived inside the silicon atom, and now there are 10 to power 18 or 10 to power 19 free electrons. Right. Now let's now look at the structure. So the structure has these foreign atoms, which is fine. They are bonding with the neighbors and freeing one electron, but there are 10 to power 18 atoms which have been displaced from the original place, and they are wandering, or they're not mobile. They're not wandering anywhere. They're just sitting where the vacancies, where they're not supposed to be any atoms. So they sit in places that they shouldn't be any atom, those free space, because the structure of a cube, let me draw the structure of a cube. Let me tell you what I mean by this. Because this is a good question, actually, Israel, that you asked. Although there's not going to be any exam question or anything on that, but these are the information that you don't easily find anywhere. Okay, so I'm going to draw a true cubic atom as the structure of single crystal silicon atom is. So that is what it looks like. So the next cell is just, the next cell is there, another cell is there, another cell there, another cell there.
Professor,
yes.
Are we supposed to be seeing the screen right now?
Oh, I'm
like,
sorry.
Were you drawing on the surface?
I'm very sorry.
I thought you were going to draw on a piece of paper and show it to us.
No. I'm supposed to be showing you the. Hang on. I'm supposed to be sharing the screen. Sorry about that. Okay. Is that good?
Yeah.
Right. So now, okay, this is the structure. This is the exact what we call unit cell of single crystal silicon. So the silicon that we were talking about is in a single crystal form, and single crystal form is like this, exactly like this. So there is another cell just like this, another cell exactly like this cube, stuck on this edge, on that edge, on that edge, on this edge. All these edges are, so these cubes are, for example, are sitting there, nicely, all in 3 dimensions. These cubes are sitting in 3 dimensions next to each other. Okay, although because the basic single cell of silicon is not that simple, but you really don't want to know, I can refer you to a textbook that you can actually see what it looks like, but it's very similar to this. And here in this single cell, there are atoms at each corner, like these. At each corner, there are atoms. I'm talking about the single crystal, each cell of a single crystal. And there are atoms on each faces. So there is atom on each face, like this. Okay. Can you see that how atoms are really placed in some kind of an order? So in a single crystal silicon, in 3 dimensions, atoms are really sitting next to each other in some form of order. and they're all bonded together, just like, you know, that they're all bonded together. Now, when a foreign atom arrives, okay, so these are bonded, these are bonded. Now, a foreign atom comes and sits there and is bonded again with the next one, and so on. Can you see? Right? So this foreign atom, the red one, is really that say arsenic atom, and all the blacks are silicon atoms. Now, this, because of this red atom, the silicon atom which was originally there has now been thrown out of its place. So where does it go? It goes, for example, and sits there. Can you see that? It goes and sits there. Did you see where I drew it? It goes and sits somewhere that is not supposed to sit. And when it sits there, what does it do? It blocks the mobility of those electrons. The free electrons initially were free to travel, to be mobile everywhere within space, empty space in a crystal atom. But now there is less room for them to move. So the mobility falls. So the huge number of dopant will bring down the mobility, and therefore the conductivity falls. So the piece of doped material, when it's heavily doped, is not as conductive. However, now let me also tell you something that it is also, I don't believe that I ever mentioned. So the relationship, let's call it, this is mobility, and this is conductivity. So it isn't that as the mobility increases, it's not as the mobility increases, the conductivity falls. That curve is not the curve that it actually exists. So the actual curve, actually, let me draw it here. The actual curve is like this. That is to say, the conductivity at very low mobility is low. Then it reaches an optimum value at certain conductivity. Now, that certain conductivity obviously means certain dopant, certain number of carriers with certain conductivity. At that point, the conductivity is optimal. And then what happens here is a different kind of issue that honestly is beyond the scope of this course. Again, but that means that at that, it reaches really that saturation, which we're not really sure how this, but the conductivity is low. See, the conductivity is fallen as the mobility increase, as the mobility, sorry. Okay, this was not the mobility, was it?
Conductivity?
Let me look this up. Let me look this curve up and come back to you this afternoon. I just hesitated for a moment. It's something similar to that. That when the number of carriers increase a certain value, the mobility falls, and so does the conductivity. I promise you, I will look this up and bring it back. In fact, you can go and look it up in Z yourself, SZE, that book, The Physics of Semiconductor, but I shall also find it in my notes somewhere, and I'll discuss it this afternoon. So that is answer. So are you kind of happy now, Israel, what's happening? So as the number of carriers increase a certain value, or after so much, beyond say 10 to the power 16, 10 to the power 17, number of carriers, then the mobility does not go hand to hand. The mobility falls, and therefore the conductivity falls. That would be the solution.
Yeah, that makes a lot of sense.
I'm glad it does. Okay. So now that we've answered one question, are there any other questions, or do you want anything for me to discuss?
I had a quick question on homework 1.
Sure. What was homework 1? I can't remember.
Or it was the one where we used the amplifier circuit and we had to choose the values.
All right. Okay.
Yeah. Well, my question was on that was what was the reasoning why you chose the 300 value, or the 300 for the capacitor, for the in capacitor?
Or the emitter capacitor, the 300, was
Yeah.
it talking about it? Okay. So can I answer this when we get to that level, because we are going
Yeah.
to discuss it.
Yeah.
I'm going to elaborate on how we choose the values of capacitors, the resistors, everything when we get. So do you mind if we just get
Yeah.
to that? Sure.
Yeah, that's perfect.
Thank you very much. Thank you.
No problem.
Right. So let me share the screen with you and begin by, okay. So now let me, before I start, you see, when we started this course, we began by telling you about everything we wanted to know about semiconductors. What are semiconductors? What do we mean by energy band? How do we discuss it? But you must, I mean, some of you may be wondering, oh, where is this going to take us? What are we talking about? Why are we discussing semiconductors? Are we studying material science in this course? But then you soon realize we could not have discussed how diodes operate without really finding out what semiconductors were. You obviously now, you know this. So it was a kind of unfamiliar kind of topic to you, some of you maybe, but then it made sense. And then you learn diode. After diode, you learn transistors. And when I said to you, transistors are so difficult to bias and to get them working right, you must wonder, why are we studying it then? Then we went to op-amp and realized, although these points that I'm just making now are very important points in your life. See, those transistors, those bipolar junction transistors, that were so difficult to operate, we collected them in a circuit and created op-amp. And you saw how op-amps could do magic. You know, how op-amps, but what were op-amps? Op-amps were a number of bipolar transistors put together. So although bipolar junction transistors were difficult to operate, difficult to bias, difficult to get right, but then inventors, circuit inventors, came and put a bunch of them together and created that fantastic, marvelous piece of IC device that we call op-amp now. So now that we review, these things must really make sense. And I want you to learn for the sake of learning, rather than thinking, you know, what are going to be exam questions? How is he going to ask me questions? Forget all those for now, please. Just concentrate on this subject and learn them irrespective of the exam. All right, so let's share screen and begin. Okay, right. So we began by saying the materials can either be conductors or insulators or semiconductors. And one way that we can, how we sort of introduce these materials, we can show them by their energy band diagrams. Okay, the energy band diagram, something like this. That means there are two energy bands for any material, any any solid or liquid or gas material all have energy band diagrams of this form, two energy bands, EC and EV. That is the valence band, and that is conduction band. All materials. Why do we say that? Because obviously, as you can see, whether it is solid or liquid or gas, they have atoms. And atoms have electrons. And electrons are either with their mother atom, with their atom, I mean, as electrons are with their mother atom, or they are free, or they have been released, they have been kind of dispatched from the atoms. They can't be anything else. If they are dispatched, they're called free electrons. So if they are dispatched, they are free electrons. And if they are free electrons, they are at that band. But if they are not dispatched, they are at this band. I want to make sure that that sentence was understood by everybody. You see, and please stop me, please. I mean, this is a review session. We have all day, if necessary, if you like. If there are anything that you're still not happy and fully grasp, please stop me, please. Just simple as that. So all I'm saying, whatever is in this world, in this universe, they're either in the form of solid, liquid, or gas. They all have atoms. These atoms have electrons around them. So these electrons may either be still with the atom, or they may have left home. They have left the atom. If they have left the atom, that means they are free electrons. They're no longer bound to the atom. They're free to travel. In which case they are on conduction band. But if they are still with their mother atom, they are at valence band. Now you may say, why? Why do they go to another band of energy? The answer to that is because they have gained energy to release themselves. So their energy is at a higher level of energy. They would not have been at conduction band if they had not gained energy. So now the question you may ask, how did they gain energy? They gain energy at least in three forms. With three mechanisms, they can gain energy, either by heat or by shining light on them or by bombarding them with electrons. So when we bombard them, we inject energy into them. So the electron bombardment goes and hits another electron, and the energy is transferred, so that electron is freed. By heating, obviously, we break the bond. They get energy by form of heat, and the bond is loosened, and they gain energy, and they go to conduction band. So they reach a higher energy level, and we call that energy level conduction band, because electrons can only contribute to conductivity when they are free. Electrons do not contribute to conductivity if they're still bound. All right. So now we agree that for all materials, we must have two energy bands called EC, EV. Now, the difference between materials is this. If this gap, which we call it energy gap, EG, we call it EG. If this gap is equals 0, this material is a conductor. If this EG is very big, by very big, I mean in the order or bigger than 6 electron volts. This material is an insulator. If this EG is anywhere between 0.25 electron volt all the way to 2.5 electron volt, this material is called semiconductor. And that is gospel. That is very, very important thing to remember, for you to know, which is not that difficult. So this gap is 0. When it's 0, that means this line, EC and EV. And that's what conductors are. EC and EV, that is conductor. Then the next class is, this is EC, that is EV, very large, bigger than 6 electron volt. This is insulator. And when this EC and this EV is moderate, 0.25 to 2.5, this is called semiconductor. We are going to discuss this today. We really are not interested in insulators nor conductors. Simple. And among semiconductors, which quite a number of materials are semiconductors, we in this semester, we're only interested in this particular semiconductor called silicon. Where EC and EV are 1.1 electron volt. See, this is what we began by describing. Okay, let me face you and tell you this again. So materials can either be conductors, semiconductors, or insulators, depending on the energy band, how far the energy band diagrams are. So if they are moderate, moderate means anything between 0.2 electron volt to 2.5 electron volts. That this range is the range of semiconductors. I do not know. any semiconductor with the energy band less than 0.25 electron volt. I do not know any semiconductor which energy gap is bigger than 2.5 electron. Having said this, I must correct myself. I mean, what I said is correct. We can deliberately engineer semiconductors with less band gap and higher band gap, but those are not existing semiconductors. Those are the ingenuity of mankind. We are powerful people, creatures. We can honestly create things. We can create, us engineers at least, we can create band gap, semiconductors with band gap outside this range that God has created. Anyhow, silicon is the subject of our talk. Because why we pick silicon? Because 99% of devices that we know are made of silicon. What are those devices that we know? Diodes, transistors, ICs. ICs are analog or digital. If they're analog, for example, op-amp is a typical one, or other form of ICs like oscillators, filters, amplifiers, intermediate filters, all these ICs which are available on the market, inside them there are devices that are made of silicon. And all digital, 99% of digital ICs are MOSFETs, and those MOSFETs in the form of NANDs, which are all digital devices. And MOSFETs are silicon. So for that reason, we only discuss silicon. Diodes are made of silicon. Germanium diodes are they're not obsolete, but they're not. Then you will find any germanium diode with some difficulty. You won't easily buy it. Still exists though. And gallium arsenide or all the compounds, compound semiconductors they're not ordinary devices. They're for special cases, which we're not really interested. Okay, so let me begin by telling you about silicon. I'd like to pause and see if everybody is happy with what I said to this moment.
Really quick, I have a question, Professor.
Yeah, by all means, please.
When you are talking about what'd you say, digital and analog, I was just curious if when we're trying to find ICs that are either CMOS or TTL, does that have anything to do with whether it's digital or analog?
Let me see if I understood you right. You're saying that ICs which are TTL, are they analog, and those which are CMOS are digital? Is that what your question?
I don't have an understanding on them, so yes, that's actually my question. You got it right. Okay.
Actually, whether the CMOS are invariably digital, and yet there are some TTL which are also digital.
Oh, okay.
Right.
Okay.
Because I mean, all the devices that we buy, I order for our lab, digital ICs, I purposely look for TTLs.
Okay.
Because I don't want you guys to go through the problem of burning them out and then not knowing what the problem is and so on. Because TTL, the CMOS ones easily burn out.
Oh, okay.
So digital devices can be found both in CMOS and in TTL form. For analog, as a guess, I would say I don't like to say things that I don't know. I would imagine they are again both
Okay.
TTL and CMOS, but see, I don't know. I mean, it doesn't matter. Yeah.
You answered my questions, so I appreciate that.
Sure. Okay. Right. But it's a good question, actually. I should find out. I mean, I must be honest, since I've come to United States and since I have kind of been separated from my research, I less find time to keep myself up to date. First 7 years of my arrival at United States, I only came to this country in 2010, and I've been with this program since. The first 7 years, I still had my PhD students from England who I was supervising them, and we still had so those have now graduated. The last one graduated to same day as Donald Trump was elected. Well, inaugurated. On that day, my last PhD student graduated. So I haven't honestly been up to date with the latest technology. So whatever I'm telling you is from 2015 prior. Anyway.
Okay.
All right. So now, are we good? So are we now familiar how we arrived at silicon and what is silicon? Silicon is, as far as us, this team, as far as we in this room, as far as we concerned, silicon is 2-band of energy. That is what silicon is. When we describe, see how different people, like for example, medical people describe a medicine in the generic form, and ordinary people or chemists name it differently. Us people name silicon as 2 bands of energy. This, to us, that should be what silicon is. So this, to us, this is silicon. There's 2 bands of energy with the gap between them, which is about 1.1. Right. Now, this band of energy, this guy named Fermi, this French scientist, he helped us by understanding this semiconductor and all semiconductors. He understood, he helped us by understanding them. He brought an imaginary energy level, I hope this is right, imaginary energy level called Fermi level, right? This level doesn't really exist. He just brought it up. He said, if this energy level is in the middle of semiconductor, this is called EF, sorry, it's called EF for Fermi, that imaginary energy level. He said, if this EF is in the middle of these two, that semiconductor is called intrinsic semiconductor, which means undoped. He just really kind of quantified this semiconductor. He said, well, let's imagine there is an imaginary energy level. That energy level can either be inside or outside, and where. So let's begin by saying, if it's in the middle, that semiconductor is intrinsic. If this imaginary energy level is not in the middle, but is closer to, for example, the conduction band, it means it's N-type. So this is EC, EF, and EV. But can you see that how the EF is closer to the conduction band? And that's called N-type. Oops. But when we say N-type, we must really mean, we must explain ourselves. What do we mean by N-type? How N-type? Okay, he said the closer this band to the conduction band, the higher the number of ends. So for example, if it's this close, it means it's even higher N. As if this, for example, is 10 to power 16 per cubic centimeter, this must be 10 to power 18 per cubic centimeter. That is what he meant. So how close the Fermi level is to the conduction band, it determines how heavily doped N-type our semiconductor is. And then he said this actually can go higher. The Fermi level can even go higher than the conduction band, in which case this material, this silicon, is doped N-type, but the name we give this is degenerately. It's degenerately doped. The same argument applies when Fermi level is close to the valence band. And how close to the valence band determines how heavily p-type material is, and the Fermi level can actually go beyond the valence band, which is again degenerately p-type doped. So now let me draw some semiconductors with Fermi level. This is EC, EV, EF, and call it intrinsic. This is going to be EC, EV, EF, N-type, and EC, EV, EF, P-type. Oops. And how N or how P obviously depends on how close this Fermi level is to either conduction band or the valence band. All right. Now that we have this far, we got this far, let's see what we can do with this. Why did we learn all this? What do we want to do? We want to create a piece of semiconductor which we call N-type piece of semiconductor. Then we create another one which we call P-type semiconductor. This material will look like this. This material will look like this. This is full of, for example, boron. This is full of arsenic. Both silicon though. They are both silicon, but then this is doped with arsenic, this is doped with boron. The energy band looks like this. The energy band looks like this. Okay, intrinsic, that means intrinsic means undoped. Intrinsic means undoped. These are doped, but N-type and P-type, which we call these extrinsic. And so we have two pieces of material, N-type and P-type. That is what the energy band looks like. All right. Because nobody asked question, I can go further, but if there are questions, please stop me. Now, I can actually stick these two pieces of semiconductors together and see what happens. So N-type, P-type, and I stick them together. So don't forget, this was full of electrons. This piece of material, this N-type semiconductor was full of electrons. This P-type semiconductor full of holes. But the electrons and holes are obviously mobile because they are free carriers in there. Now, free carriers have mobility. That means all these electrons in this material, they can travel, they can actually move. I'm now drawing in what's inside an N-type. This is what's inside an N-type material. These are all electrons that they can travel, they can just travel everywhere. They can just go everywhere within material, just travel everywhere. They can go anywhere. The exact thing happens inside the P-type material. They're all holes everywhere, just full of holes, however number that we have created. For example, we have got 10 to the power 18 electrons, 10 to the power 18 holes, and they can also travel everywhere. They are mobile, they can fizz around as much as they want, anywhere they want. That is true. That is true. I'm not just saying it. It is actually what happens inside a piece of silicon. The two of my cards here. A piece of silicon, N-type, P-type. And these two have carriers inside them, and the carriers are mobile. They're free. They travel everywhere. Now, when we connect them together, and these electrons can really travel. Of course they can travel. They can go anywhere and enter this material. Electrons can go and enter here. They just travel anywhere. Can you see that? And so can the P-type. P can also go there, can go there, can go there, can go there, can go there, right? Because they're free. And if these two are stuck together, that means there is no obstruction for them. They can travel, of course they can. But now, let's see what happens. So this is N and this is P. So these electrons that can travel there, as soon as they enter p-type, they marry. An electron finding a hole, what happens? They annihilate. And they're neither electron nor hole. See, when this electrons travels here and find a hole, they're no longer electrons nor holes. Why do we say this? This was the original atom. This electron left the mother atom and a hole. This became a free electron, and what was left was a hole. Now that it comes back and meets, there's just nothing. Nothing, by nothing, I mean they're no longer carriers. They are the atom that they were in originally. That is also something that we must all learn. So the electrons which travel towards the p-type and met a hole, they annihilated. Poof, nothing there. No longer exists. And all is left are just atoms. Yes, Israel.
I guess I'm wondering, is there a more concrete way that that's usually, I guess, explained? Because, like, I mean, it makes sense since they're both equal in charge that I guess they sort of annihilate each other, but, like, you're saying they just turn back into the, like, now, because they're neither electrons nor holes, which I assume you mean they don't have those specific charges. Or are they just like the neutral? Because you're saying they turn back into the atoms, but like they turn back into their respective arsenic or silicon atoms, or what do they?
Well, atoms are not different from, I mean, if, for example, in that region, whether there are arsenic atoms or silicon atoms, what difference does it make? Atoms are all the same. It's only molecules which are defined under the term of arsenic or silicon. But once they're atom, they're all the same. So it's really it's not of any interest for us to know whether they go back into arsenic form or silicon form. That doesn't give us any knowledge, any information that would be beneficial to us. It does not matter at all. The fact that they annihilate and they're no longer electron nor hole tells us that there are no more carriers with charge. So that in that region, we just have no more carriers. When electrons meet holes and they just annihilate, I'm calling it puff, I'm calling it nothing. That means no more carriers. That's what I'm trying to say. So what remains is really none of our electrical engineers' interest. To this level, we were interested to know what happens to these carriers. But now that the scientists tell us that they're no longer carriers, they don't exist in the form of carriers. Why are they no longer carriers? Because they don't have charge, they don't have mobility, and they don't have mass. Therefore, they don't exist. We don't want to know. But I can also go just a bit further as a physicist. Now, that was the electronic engineer The obviously electronic engineer studies the knowledge of electrons, movement of electrons, so that, but as a physicist who wants to know exactly what happens, those annihilation, that the energy of required, that the energy that electrons did have and now has joined in with the whole, and so what happened to the energy then, you may ask? That energy that was given to that electron, I don't want to confuse you, I just want to give that extra knowledge for you to think about it. The electron was given, the initial electron of an atom was given energy to become a free electron. And now it has gone back to its original place. We call it nothing, right? So what happened to that energy we gave it then? The energy we must be questioning about. That energy has been freed by form of light. It's not a light which is good to anybody. That light is not detectable, is not achievable, is not usable, is just nothing. But the energy has been transferred into form of light. If it was in a direct band gap semiconductor. But then if it was the indirect, which we remember, we studied direct and indirect band semiconductors, those semiconductors which were direct, that energy was converted into light. The indirect semiconductors, the energy was turned back into heat, phonon. That is the answer, but the answer is for physicists, not for electrical or electronic engineers. As far as we're concerned, this annihilation left no carriers, no more carriers, no more charge left, no more mobility, no more mass. That was it. Right. So the electrons come here and they annihilate, and so do holes. And therefore, let's say within a vicinity, within a region, within this region, we will have no more carriers. It has this region from carriers is really depleted from carriers. And that is an important information to us. Depleted from carriers, but does not mean depleted from anything, just depleted from carriers. No carrier exists there. No electrons, no holes. But they were ions. There are some ions. Why? Let me answer that question. Why are there ions? In a piece of N-type silicon, that these atoms were all sitting there. I'm just going back one stage for you to see what I mean by ions. See, originally, this p-type that I'm talking about, N-type, this N-type material, all this N-type material, it was like this. And all electrons were like this. This is how our N-type material was originally like. But then in this structure, and so on, in this structure, they were foreign atoms because it's N-type. Because N-type, there are foreign atoms. Now, these foreign atoms had free electrons. When this atom had freed one electron, this is called ion. It's a positive charge, positive charged ion. That is called positive charged ion. Because it has freed an electron. This foreign atom freed an electron because this is arsenic. Arsenic has 5 electrons. 4 of them were bonded with the neighbors. 1 was freed. 1 electron was freed. This atom originally had 5 electrons. 4 of them were bonded with the neighbors. Then there was a free electron, freed. This electron that left this atom, what was left so the electron was freed, what was left was an ion, a positive charged ion. So the whole of this material were full of electron carriers. As well as these carriers, there were 2 other things in there. 1, just atoms, like this one, this atom. 2, there were ions, like this one. This is an ion. And as well as all those, there were electrons. So the free electrons that had mobility, but atoms and ions have no mobility. I'll bring the face back, the screen back if you want. But so in that piece of silicon material, N-type, there were 3 things. There were more than 3 things, but 3 things are important to us because there are defects, there are holes, there are all kinds of stuff. Fragmentations of these molecules, all kinds of garbage. But at least
some things. There were 4 atoms. There were some atoms which were single atoms, which were not even touched. And there were also ions which were floating.
Correct. These were the 3 items which were in that piece of semiconductor N-type. So this N-type semiconductor, this P-type semiconductor. So when we say this region is depleted from carriers, at least we can say depleted from carriers. But one thing which is left in there, 1, atoms, 2, ions. Right. Atoms are neutral. That means nothing. Ions have charge. And therefore, in there are positive charge And in there are negative charge. These charges in there and in there create electric field. This electric field is not measurable. We can't measure it. You know why we can't measure this? Because how do we measure? We have to obviously have a probe to go there to there. We have to connect some probe to measure. As soon as we put a probe, they annihilate. They just disperse. So it cannot be measured, but we can detect it. There is an electric field. That electric field exists, and that electric field is enough to prevent these electrons and these holes to travel any further. They deter. This electric field will deter holes that way, will deter electrons that way. Please understand, we have not spoke of any bias yet. We have not connected any battery. We have not applied any energy yet. This is the pure physics, the science of the material that it brings that about. So the electric field created will not allow holes to go, electrons to go. It's just remain the way. That depletion region is an important factor about this diode, about the PN junction. Sorry, not diode, PN junction. Any questions so far?
Dr. Kasai,
Sure.
is this electric field created by, how you mentioned annihilation? Is that created by that, or is this created by something else?
The electric field is created by the positive and negative ions.
Oh, okay, okay.
You see, in each material, in a piece of, say, this piece of N-type semiconductor, similarly, another piece of P-type semiconductor. In each of them, in each of those, there were three commodities. Let me mute so we can't hear you, dog. So that's what I've muted you, right? So in each piece of material, there is obviously in the entire piece of material, there are free electrons, there are atoms, the silicon atoms, which were there originally, and they were ions. The electrons are still free. Well, in that region, all electrons have been annihilated. No more electron in that region, in the depletion region. But the two other things are still there, ions and atoms. Atoms are neutral. Atoms have no charge, so they're not really bothering anybody. Neutral. But then the negative charge of ions on one side with the positive charge of ions on the other side create electric field. It's the ions which create the electric field.
Thank you very much, Dr. Kasai.
You're most welcome. You do have a noisy dog.
It's my rooster. I'm sorry. It's a rooster. I have a rooster. It's my rooster, not my dog.
Oh, sorry. Oh my God. Fantastic. Right. So the dog must be annoying that. Anyway. So, yes. Actually, it's so difficult to distinguish a rooster's sound with a dog. I honestly thought it was a dog.
My dogs cry they don't bark, they cry.
Right.
They can't bark. I have French bulldogs, but yeah, it's my.
Well, I heard in England, I don't know if you know, the England, the staying home is more strict than here. And people have found, especially in London, that deers and goats and all that are entering people's homes. And some people are actually taking goats as their pets, and they walk to supermarkets with them. So they just carry the goats with them wherever they go. These are God-sent goats. They've just entered the city. Anyhow, this virus is doing a lot of peculiar things. Okay, so let me just continue. Right, again, we have connected this two pieces of material together, and we have created a region in the middle, which we call it depletion region. And this depletion region, that means depleted from carriers, depleted from carrier. This is depletion region, call it D, and D for depletion. But for example, if this is N-type, this is P-type, then here is positive ions and negative ions, and they create electric field, which they don't allow carriers to travel anymore. So this is still N, that they are full of N, full of electrons. Here, this material is still full of electrons, like this, and this is full of holes all the way. So the material is still the same. These are full of holes, and sorry, that is full of electrons. Anyway, and that is our semiconductor now. That is our p-n junction. There is a junction. There is a junction. Just on the near vicinity of this junction, there is a depletion region. From then on, there are just two pieces of material, N-type and P-type. Now, let's draw the energy band diagram of this. Okay, that was N-type, and that was P-type. When we connect these together, what happens? We obviously connect them together. That means they just go exactly like this, again, exactly like that. We connect them together. Okay, this P-type remains as P-type, and that N-type remains as N-type. But then in the vicinity, in the actual, what happens between there? What happens to the where is the Fermi level in that region? What happens to the Fermi level here? Oops. The Fermi level does this. But in fact, when it does this, what happens to the bands of energy? Because the Fermi level should have really stayed like this. Okay, actually, let me give you an example here. when we have a glass of hot water, a glass of cold water, and we pour these together. We create some sort of pipe between the two, so we create some sort of connection between the two glasses of water. So the water now, is it hot or is it cold? It's neither hot nor cold. It reaches that kind of equilibrium temperature. It arrives at a new phase in terms of temperature, which is called equilibrium. Now, the same thing happens with the two charges. So when we connect an N-type with P-type, the Fermi level stay the same. That means the band bending takes place. So can you see that is P-type. That is N-type. But then, as we start from here, the Fermi level is still very much like the N-type. See, I am now traveling from there to there. I want to know what happens with the Fermi level as I travel from there to there. I want to know what happens at that region. So I'm starting from here. My Fermi level still N-type. The material is N-type. Then when I enter the depletion region, my depletion region starts with N-type. Then it becomes less and less N-type. Becomes less and less N-type. Why? Because now the Fermi level and the conduction band gets further and further away. So there, I'm even further than the Fermi level. Remember when we said that the Fermi level, remember we said the distance between the Fermi level and the conduction band determined how N-type this was? So I'm getting further away, the conduction band, further away from the Fermi level. At that point, I can say that the distance between Fermi level and the conduction band is the same as the distance between the Fermi level and the valence band. So I'm becoming further away from the N-type. Here I become kind of intrinsic, and there from then on I become even P-type, because now the Fermi level gets closer and closer to the valence band. So this is the Fermi level changes from one end to another. And the material, which was N-type this side, became less and less N-type, less and less N-type as we go along, became kind of undoped at the junction, more and more P-type, and then absolutely P-type there. Did everybody follow that?
Professor, I got lost real quick on something on that diagram.
Sure. You want me to bring it back? Yeah.
Can you?
Yep, please. Yeah.
It was just a very small thing.
Yep.
So you said the distance from the Fermi level to the conduction band is going to be the same distance from the Fermi level to the valence band. And that lost me because if you look, I don't know if it's just the drawing, but they don't look the same to me. Can you show me how they're the same? I see they're the same in the middle. That's the only part.
Right. Yeah. Okay. So can you actually, okay, let me use cursor. this line I just drew, this line
Okay.
is the actual junction.
Right.
And at that point, the distance between this Fermi level and the conduction band is the same as this distance between the Fermi level and the valence band.
Oh, just at that point, you're saying.
At that point.
Okay.
In fact, I'm talking about exactly at that point.
Got it. Thank you.
Now, before this, at this side, I'm saying that the material which was originally n-type, it became less and less and less n-type as we go up.
Right.
But then when we reach here, which is at that, I mean, in this whole region, I'm talking about this depletion region. At this depletion region, the depletion region was kind of n-type here, but then it became less and less and less n-type. And now is moving towards more and more and more p-type.
Right.
At this point, it suddenly becomes absolutely p-type. That is what I'm trying to say.
Got it.
Yeah, very good, very good. That was actually a very important point that we had to clarify. Thank you very much, Isaac, for asking. Okay, so that is what happens in a junction. That is what's happening in a N-P junction. That is really, this is what's happening in that PN junction. Okay, great, so far so good. Now, this was obviously with applying no external energy, no battery, no bias, nothing. This was just a pure piece of a connection between an n-type and a p-type. Now, we can apply some external battery. N, P, and we are going to connect battery like this. Of course, we can connect this battery this way, or we can connect it, for example, this way. I mean, this is the negative pole of the battery. This is the positive pole of the battery. I am going to, this time now, initially, I would like to connect the negative pole of the battery to n-type and the positive pole of the battery to p-type. This way of connection is called forward biasing. Forward biasing. I purposely do this time. So I'm connecting n-type to n-type, p-type to p-type. And what happens? Don't forget, we did have depletion region. And now these electrons which were there, these are electrons, this is negative pole of the battery. They are same charge. This battery is the same charge as these electrons. Equal charges repel each other. So these electrons are all repelled to further and further towards the depletion region and forced their way towards the depletion region, making depletion region narrower. So the depletion region, which was originally wider, it was this wide, is now becoming less wide. This line is the junction. Depletion region was originally there. Now by me connecting the battery, it was less wide. Holes, exactly the same again with holes. This positive charge same charge as the holes, obviously then they are repelled and the depletion region becomes narrower. So the depletion region, which was originally this far, this wide, that was the original depletion region. Without the bias, it was this wide. Now it's becoming this wide. And this depletion region, which is now this wide, I am going to increase that. You see, that was I applied just a bit of battery there, and that's what happened to originally. I was just applying small amount of voltage. By a small amount of voltage, I mean maybe 0.1 of a volt, 0.1 volt originally. What was telling you, I was just applying about 0.1 of a volt. Then I take this to 0.2 of a volt. Would you agree that the depletion region will even get narrower? So now the depletion region on both sides gets really narrow. And then when I increase this to 0.7 of a volt, at 0.7 of a volt, that is what happens. NP 0.7 of a volt. I have no depletion region whatsoever, although I'm showing this junction, but really the junction doesn't exist either. Correct? Because if they are both material, what am I talking about? That is my diode. When I connect battery, that is my diode. Now, if this is the diode, would you not expect some current to flow? So now I want to plot I against V. So initially, as the voltage was 0, there were no current flow when the voltage was 0. When the current was a small, 0.1 or 0.2 or 0.4, say 0.4, no current. 0.6, 0.7, then current. That is 0.7 of a volt. Now this current that flows now is really sufficient amount of current. It's the maximum amount of current. As much as there can be current, which now that current is no longer determined by this battery anymore. It's determined by the number of carriers, by how much dopant there was in there. So the current becomes independent of the applied voltage.
Can you repeat that?
Of course I can. Of course, right. Let me actually repeat it here this way. I had this PN junction with this depletion region and this kind of battery. which I'm going to alter. This is N, this is P, and this is without, this is at the moment, the voltage is 0. So N-type, P-type, depletion region. So far, so good. Now I'm going to apply V equal 0.1 volt. These electrons, they were full of electrons there, electrons everywhere. Electrons were repelled, and that is now the new depletion region. Depletion region became narrower because obviously these electrons were repelled. So now, would you say that depletion region gets narrower? Now the same argument exists because these were holes, positive charge, at the same time. At the same time as I am applying this 0.1 volt, obviously 0.1 volt means 0.1 volt here, 0.1 volt there. So now this side, the depletion region gets narrower. Now I'm going to apply V, say 0.4 volt. Would you say that the depletion region gets even narrower?
Definitely.
Gets this narrow. Right. And now when I apply V equal 0.7 volt, no longer depletion region exists at all. Depletion region just vanishes. All electrons, all holes. Electrons can travel because of this battery, and a current will flow in that. So if I put an ammeter there, and there is a needle, that ammeter will deflect. When I apply 0.7 of a volt, I will get current. I will get current there. I will get the current I to flow from there to there. The circuit will close. If that is the case, remember I applied 0.0, 0.1, 0.2, 0.4, 0.6, all the way to 0.7. I just want to now plot that. And plot by plotting current there and voltage there. Voltage in volt, current in milliamp. I am saying, when I applied 0, there was 0 volt, 0 current. Then I applied 0.1, 0.2, 0.3, 0.4. I got no measurable current. Then as soon as I reached 0.7, I suddenly saw current. That is 0.7. Now, here, the current that is flowing there is really nothing to do with the battery. The 0.7 or 0.8 or 0.6, whatever that is. That voltage is sufficient for this current to flow. There will be full current flow, and the amount of flow of current is really how many carriers we have, how heavy N is, how many number of electrons. That is what I meant. How good are you, Isaac?
I'm good. That made sense. So you're saying how heavily it's doped, the
That's
current
right.
is dependent on that.
That's correct. Independent of the voltage.
Interesting.
Yeah. Now let's see. This is obviously this graph is what we see. We can actually measure this. I mean, this is what we can apply voltage. We apply voltage there, and we measure current. I mean, there is no magic about this. This is nobody's. I mean, even if it was nobody with any knowledge of what goes on inside PN junction, we can apply voltage and measure the current. So it's not really anything magic about this. This is what we measure. When we can measure, we can't argue with it. It's just what we measure. Now let's see what we measure meets or sort of correlates with the mathematical relationship that we know about at PN junction. Mathematicians, before they actually could make any measurement, mathematicians came and told us the current through a PN junction will be the I. Current through I is equal I0 E exponential to the power QV over KT minus 1. This is what mathematician told us. What did they mean? They said the current through a PN junction is equal to some small leakage current, some constant value, multiplied by exponential the charge of electrons times the applied voltage. This is I diode. This is V diode. This is the V that I applied. That V is this V. That I is the I that I measured. So they say ID is equal I0, Q being the charge of electron, times this applied voltage, divide by Boltzmann constant times the temperature. That means the carriers have a lot to do with this. Minus 1. This is what mathematicians told us. Right. But now, can you see that even when, okay, this Q over KT, we can substitute values for it at room temperature is 26 millivolt. That's 26 millivolt. Now, let me just apply, for example, let me just say I am applying VD to be 0.7 of a volt. Let's just substitute these values here. So ID would be I0. I0 is a nominal value, which we're not really concerned about right now. It's just a constant for now. Exponential 0.7 times 0.026 minus 1. Let's see what that makes. Let me see if I can measure that. Oops, not this one. Where? Point 0.7 times 0.026. I don't have e to the power. I don't have, unfortunately. Let me see if I can get. Why can't I get this scientific one? Oh, on this, I don't have it. Anyway, doesn't really matter. But my point being Can you see that if I just increase the voltage from 0.7, say I take it to 1 or 1.2 volt, then this exponential term will so overwhelm this 1 minus 1. That is massive because it's 2.7 to the power of whatever value. I don't know, say 2 or 1 or 1.5 or 2 or 3, whatever. But then we can forget, really, we can forget the minus 1. Minus 1 in comparison to this is negligible. So we can say that ID is proportionally proportion to VD exponential. And that is an exponential increase. That is my point. So what we measure meets the mathematicians. What they told us were right. And what we understand is also right. That was really looking at this against what mathematicians told us. Let's see what the energy band diagram tells us. Remember, we said that this was our p-n junction at equilibrium. That means no bias. That is exactly what happened. Now we are applying this to the n-type and that to a p-type, a battery. So we are applying that kind of relationship. So we're applying voltage connecting n to n-type and p to p-type. What happens to what happens to the energy band diagram? In fact, the energy band diagram at Fermi level breaks up. So now at the end, when we apply that goes up, the Fermi level, this is how much applied voltage I applied, forward voltage. But can you see now the electrons can really travel? I mean, they couldn't. The electrons here, this was too steep for them to climb this much. From there to there, it was just too steep for them. But now this is less steep, less steep. That was, say, 0.4 volt. When I apply even higher, this Fermi level is now the forward voltage, VF is about 0.7 volt. And now the electrons can easily travel. There is no barrier for it. I only showed this much because I wanted to show you the barrier. So there's no barrier. There's no barrier. The electrons can easily travel. So with in terms of energy band diagram, in terms of mathematicians, and in terms of the measurement, physical observation, we can see that when we apply forward bias to a diode, there will be current flow. And a current will flow like this. And that is called the IV characteristics of a diode. Now let's see what happens when we reverse the polarity of the battery. Because whatever we say that we observe with mathematicians and with the energy band diagram, if it is true, when we reverse the bias, reverse the polarity of the battery must also be true. Otherwise, we haven't proven anything. So let's see if it's true. Any questions so far? Let me stop and ask any questions. Good. Isaac, are you following?
Yes, sir. Now you're going to do the reverse bias.
That's what I'm going to do. Yes, thank you. Yep. Right. So let's just see what happens. Here we proved it. Let's now reverse the polarity of the battery. Again, NP, depletion region. Now we are going to change the polarity. That means this is positive. These were electrons. And these were holes. Now this is negative, that's positive. Can you see that now that the unlike charges pull? That means because there is negative pole of the battery here, all these holes will be attracted towards this, and therefore the depletion region will widen. This was the junction. The depletion region now widens, and so does this side, because the positive pole of the battery attracts electrons, and now the depletion region widens. This is that much voltage. How about applying, this is, for example, say V equal 1 volt. I'm just making up 1 volt. And then I'd like to apply high voltage. Say I apply 10 volts. And see what happens to that. I can see that the depletion region gets even wider. That's all of that is depletion region. Why? Because now V is 10 volts. All these poles are really pulled towards this. All these electrons are really pulled towards this. So the depletion region gets really widened. Depletion region widens even further. I can increase this to 20 volts. The depletion region widens that much that it suddenly breaks. When it breaks, there's obviously no more depletion region. That means, just like the previous case, there will be huge flow of current from there to there, because we always show from negative to positive. So there will be huge flow of current there to there. So if I was to plot the IV, that is IV, which the positive was like this, the negative can go like that, and then suddenly like this. Let me plot it nicely. Sorry. Because I can't rest my rest on anything. That's why I can't really draw the straight line. I V minus I minus V. That is the true IV characteristic. From here, that it actually a lot of current will flow and the diode is ruined, is broken. We're not interested in that part. So the IV characteristic really is this far. Now mathematicians who told us I equal I0 E Q V KT minus 1. Now look here, when this becomes negative voltage, the higher the voltage, the less becomes this term, and minus 1 becomes more pronounced. So this gets 0.9, 0.8, 0.7, 0.2, 0.0005, 0.000009, and so on. So the result, I equal minus I0 times some numbers. So the higher the voltage, the less, the higher is the reverse current. The higher the voltage, the higher is the reverse current. So what mathematicians did say, it matches what we are saying. Depletion region widens and widens and widens, less and less current. There is no current. When depletion region widens, no current. Simple as that. Let's look at the energy band diagram now. Again, N-type, P-type. Connect them at equilibrium means no bias. Oh my God. Now I want to connect them with no bias. That was where there was no bias, and that was the depletion region. Now we want to apply reverse bias. Remember when we apply forward bias, this Fermi level went up, this Fermi level came down. That was for forward. Forward was like this. That went up, that came down. Now we want to apply reverse. That means this will go up. That is V reverse. Between that Fermi level and that Fermi level, I'm applying reverse. Now, the electrons which were here, they could not even climb that much. How can they climb this much? There is no way the electrons can climb here. That means zero current. Oh my God, it's already 12 o'clock. Oh, bloody hell. Sorry. Sorry, excuse my language. Actually, we went too long with this. I was hoping to even finish the transistor by then. Okay, I guess we should hold here and go. We can. Do you mind if we spend 2 sessions this afternoon? You do mind?
That's fine.
That's fine.
I meant to say,
don't mind at
no,
all.
that sounds fine. Yeah, that sounds
Okay.
great.
So let's go have 1 hour, come back at 1, spend 2 hours to see how far we can go, and then stop maybe for another 30 minutes or 1, and then come back again. Hopefully finish the review today. I'm sorry about this. I just went on and on and on too long. But are we good to this level? So now what we as electrical engineers can measure meets what mathematicians told us about the relationship. It actually meets, makes sense. And also when we hit it while we measure or we examine this